During the last class, we were talking about motion diagrams and diagrams that you can use to represent the motion of any given object. What are we going to do today? Okay, just knowing the position at any given point in time, we are going to create tables and graph, and then we're going to read those graphs just to get more information about the motion of the object. In addition to describing the motion of the object by reading a position versus time graph, we are going to analyze the motion of more than one object. And that is when you will have to apply what you know about a system of linear equation. Because for this part of the course, we are going to be addressing objects that are moving at a constant speed or velocity. If you have an example here, okay, I was posting this with your notes. You know that this is a table, but a table is not very useful. Why? Because you don't see the relationship, even though you can see over here that the position every 1 second, the position is changing by 5 meters. Okay? Even though you can see that on that table, and you know that we use table to organize this information, we are not going to use just table to get the information, because when you look at the graph, from the graph, you can get more information than from the table. Okay. This is your graph over here. In your graph, your independent variable always is gonna be the time. Okay. So if you are taking pre-calculus or you took Algebra 2 last school year, you know that you can use function notation here, because since time is the independent variable, you can write an equation to express position in function of the time. Okay, this is your graph over here, and in your graph you're gonna have the origin or your point of reference, or the starting point. Okay, that point, the time, see the order pair that is represented, that point is 0.0, seconds equal to 0, position equal to 0. Okay, and then this object start moving, okay, at a constant rate. How do you know that your object is moving at a constant rate? Because it is represented by a line. If you have, okay, let me use another color, a curve over here in your graph, you don't have, okay, a constant rate, and then you'll see what you have to do when you have that situation. Okay, but for now, what do you have here? You have your position, you have your time, you have your point of reference or the origin, and an object that is moving at a constant rate. Why? Because it is represented by a line. Questions about that? Okay, I'm assuming that you don't have questions about that. Instant position or instantaneous position is the position at any given point in time. So I want to know the instantaneous position after 4 seconds. I go over here to my independent variable 4 seconds, all the way up to my line, and then I go all the way here to the left, 20 meters. What does that mean? That after 4 seconds, my object was 20 meters away from the point of reference or the starting point. Okay, Ms. Ramos, you're teaching us this like we are in second grade and we don't know anything about the slope. We know that this is a line and that the slope is positive. Okay? What does that mean, Ms. Ramos, that the slope of this line is positive? It means that the object, let me continue down here, positive slope means that the object is moving away from the starting point or the reference point. See that? Now, let's say that moving away from the starting point. Ms. Ramos, if we have, let's say that we have a line. Okay, my goodness, I don't know. We have a line with a negative slope. The object is not going to be moving away from the starting point. See, you have this case over here. Okay? The slope is going down, but since you're starting the origin, okay, you are moving away. Now, how do we know, okay, the difference between negative and positive slope to say that they are moving away? So I have to give you the direction. In this case, it was moving, okay, northeast. In this case, it was moving southeast, okay? Positive and negative away from the starting point, but I have to give you the direction. Okay, I have to give you the direction. Now, let's say that you have another situation. And you start over here. Let me use another color. Over here. And your line is going down. Ms. Ramos, in that case, what's going to happen? Okay, see, as you can see, your object start moving 20 meters away from the point of reference because, see, this is your point of reference. Your object was located 20 meters away from the point of reference, and then, since you have a negative slope, okay, your object start moving towards the point of reference until passing the point of reference and continue moving in that direction. Okay, so one more time. It's positive. If the slope is positive and you have this situation, it's because it's moving away from the point of reference. But if you have another situation in which another quadrant of the coordinating system is used, you're going to have a negative slope, but still it's going to be moving away from the reference point. So you need to analyze the graph that you have in there. A negative slope also means that your object didn't start at the reference point, that start like meters away from the reference point and is moving toward the reference point. So those are different situations that you may have in there. Okay? Questions about that? No? Another possible situation, and let me use another color here. Okay? Let's say that you have, see, a line like that. What does that mean, Ms. Ramos? That your object didn't start moving at 0 time, okay? That your object start moving after 5 seconds pass and then start moving away from the point of reference. Those are the different situations that you can have in a graph of position versus time. Questions? No? With an X. Ms. Ramos, why were you screaming, just explaining the different situations that we can have in a graph of position versus time? Because you're going to be solving problems that involve the motion of an object given a graph. That's what you're going to do. Okay? And then you need to know how to analyze the graph of position versus time. See? We start with one object, but you may have 2 or 3 objects in the same graph, And if you know how to work with system of linear equation, you can find the point at which the three objects are meeting. Okay, so this is a practice problems that you have in your book, and I think that you have that on your notes too. Okay, so as you can see over here, this is what I was explaining before. See, time is your independent variable over here, the position is your dependent variable over here, and this is your reference point. We were talking about that the other day. Okay, anything to the left, negative, it doesn't mean that you are walking in a negative number. That means that you are walking in the opposite direction. This one is the east, this one is the west. Remember that position has a magnitude and a direction. Okay, so over here, that means that you are going, the positive part means that you're going all the way north, and then over here, when you're going down, you're going all the way south. Okay, so if I'm here in Miami and I'm going to Orlando, I'm gonna be moving on the positive part. But if I'm here in Miami and I'm moving all the way to Key West, I'm gonna be moving on the negative side of the rectangular coordinating system. And all of that depends on your reference point, because if your reference point is Key West, if you go to Orlando, still you're gonna be in the positive side. But if you stay there, or if you are here in Miami, okay, and you move to Key West, or you are moving to Key West, and Key West is your reference point, you're still moving in the positive side. Depends on the reference point. Reference point is super important. Okay, so here you have, you see, I'm not going to read the question because I'm going to analyze the graph. This object over here, let me erase all the garabatos that I make over there. Okay, this object that I have over here, if we are going to assume that this is half, so 125 meters, is located, so initial position, if you know that initial position is represented with the X, E is subscript, I subscript in there, even though you're going to represent that in the Y. That's one of the misconceptions that you have when you're using the formula. Even though position is represented on the Y-axis and is the dependent variable, you're going to, okay? So initial position is, let me see, 125 meters. The line is going down. What does that mean? That the object, see, was moving towards the point of reference. The point of reference. If you look over here, after 5 seconds, okay, the object was located, you're going to put final, see, it's not the final one, but I'm going to put final, was located in 0 meter, because it was passing by the point of reference and continue all the way south in that direction, moving at a constant rate. Understand that part? Okay. So knowing that, we are going to start answering the question that you have over here. It says over here that the graph in that figure 12 represents the motion of a car moving along a straight highway. Describe in words the car's motion. I already did. Okay, so a car that started at an initial position of 125 meters away from the point of reference is moving toward the point of reference. See, that's how you're describing that, because we're not talking about speed. See, until now, you don't know how to calculate the speed, you don't know how to calculate velocity. So we are not going to touch those terms right now. Say, draw a particle model. Particle model, not a motion diagram. A particle model is the one a particle model debe ser an emotion diagram that corresponds to the graph. Okay, particle model. Okay, so you know that a particle model is the one that is using a dog. Okay, the motion diagram is the one that is using a picture. Okay, you remember that the object, when you use a particle model or motion diagram, you are representing the position of your object during constant intervals of time. So it's up to you. You can make that over here every 2 seconds, or you can make that over here every 1 second. I'm gonna pick a second. So I'm gonna start over here. Wait, let me see. I'm gonna start a second. When the time is equal to, let me start over here my particle model. So I'm gonna start over here, time equals 0, and then I have position is gonna be equal to 125 meters. So now time here is equal 1 second, and in 1 second, okay, I have to go over here. And I need to find the position. Okay, around 90. So position 90 meters. See that? Yeah, I will do that for 2. Time equals 2 seconds. See? Yeah, I have to put the position over there. You can do that for every second, for every 2 seconds, or for every 5 seconds, depending. Now you're gonna do the same with the motion diagram. But instead of using a dog, what are you gonna use? You're gonna use the car. A picture of the car. Okay? So the time interval has to be the same. The vectors that you have here representing the displacement are going to be the same. Probably because when you have a straight line, the object is moving at a constant rate. Probably not for sure. Otherwise, you wouldn't have a line. Okay? That's a way that you can use to check that your answer is correct. If the position versus time graph is represented by a line, you're going to have constant interval of displacement when you're using constant interval of time. Okay, that was 12. Okay, so I answered this one. Okay, 13. It says over here, answer the following questions about the car motion. Assume that the positive x direction is, see? Now they're giving you more information. The positive x direction is of the origin, and the negative direction is west, meaning that we're going from west all the way. No, the positive is, let me see. Assume that the positive is, meaning that we're going from east to west. Because according to the information that I have over here, we are going to assume that the positive part of the position is east, and that the negative x direction is west. At what time was the car positioned 20 meters east of the origin? 20 minutes. This is the east part, the positive part. So 20 meters, 25 meters. How you gonna find that time? Oh, mi madre, you learned that when you were in math. Pam, pam, pam. And then you go down. When you touch the graph, you go down. And that answer is there. So 1, 2, 3, 4 seconds. Okay, so for 13, A, after 4 seconds, because over here in seconds, my car was 25 meters east. See that? Of the origin. Where was the car at time equal 1 second? Do the same. See? And we did that. Over here, 1 all the way up until we touch the line. And when we go over here, okay, it's around 90 meters away. Okay, B, 90 meters away or, now that I have more information, east of the origin. See that? Because now I know that the positive part is the east. Okay. So question C over here is asking you for what was the displacement of the car between time 1, when the time it was equal to 1 second, and the time was equal to 3 seconds. Displacement, okay, between 1 and 3. So I'm gonna look over here. If I go back, no, if I go all the way, this is very difficult, to the left. If I go all the way through the left, okay, I'm gonna assume, see, 1 over here, and then I go here, 3, I'm going all the way here, I'm gonna land here in 50. This is my displacement. 90 minus 40 minus 50, that's gonna be equal to 40 meters. That's the displacement. Now the car was moving west. The displacement was 40 meters west, because it's going all the way through. See, this one is not 40 meters, is the location. Location after 3 seconds was 50 meters east. Still the displacement is pointing to the west. So 40 meters to the west. Understand that part? Okay. All of this just to read in the graph. Now we are going to introduce another object into this situation. Questions? No? Okay. Okay, for this practice problem, we are going to complete 16 all the way through 19. Okay, 20, no, we're not going to complete that. We are going to complete 16 all the way through 19 because problem, a ver, let me see. Oh, no. You know what? Change my mind, because I don't have the picture over here. I have to use a picture from another problem. So, yes, I'm going to do the 20, the difficult one, according to the difficult one. So I'm going to do the difficult one. And now you have, in this picture, you have 2 objects or 2 persons that are moving at a constant rate. I don't want to talk about speed because still you haven't learned about speed. But you know that when you have a line, okay, that means that that object was moving at a constant rate. And the slope of the line is representing that rate. So you have over here Juanita. Yeah, I'm going to put over here Juanita. Yeah, I'm going to put over here Heather. I'm not going to answer the questions. I'm going to look only to the graph. Time over here, and I have position. Okay, Juanita. What can I say? How can I describe Juanita motion? Okay, so Juanita, you look over here, and let me make that bigger. Juanita started over here at the reference point or at the origin. Now, Heather, did she start at the origin too? Yes. She started at the origin too, because over here the x is gonna be, the position is 0. Now, do they start at the same time? No. As you can see over here, let me see, 1, 2, 3, 4, 5. That's super important when you are analyzing graph position versus time, that you find the scale. Every rectangle in here is representing, in the x-axis, is representing 0.1 hour, because that's the unit of measurement that they're using there. Over here, 1, 2, 3, 4, every line in there in the y-axis is representing 1 kilometer. Okay, super important. So Juanita start at the origin. Okay, time 0, position equals 0. and she start moving at a constant rate. Now Heather start 0 hours later, and she start moving at a constant rate. Okay, that's the only thing that I can say right now about them when I'm looking at the position versus time graph. Now I'm going to start answering the questions that I have over here. Say, Juanita goes for a walk. Later, her friends Heather, see, they are giving you a hint. Okay, that's why the lines, they are separated. Later, her friend Heather started to walk after her. Their motions are represented by the position time graph in figure 15. Okay, how long had Juanita been walking when Heather started her walk? That's super simple because Heather started over here. So Juanita, y I'm putting that big so you can see that Juanita was only had covered that distance. Okay, if we are gonna assume that that point over there, so you don't have it there, is 0.5. So how long has Juanita been? How long? Okay, but they're not asking for that. They're not asking for the distance that Juanita was walking. They are asking for how long Juanita had been walking with Heather started to walk. So time over here, I'm going down here, 0.1 hour. Okay, so Juanita, let me put it over here. Juanita, let me erase it, had been walking for 0.1 hour. You can see that there because if I erase all my garabato, all the things, ay mama, no. Oh my goodness, I cannot go back, right? See, if I erase all the things that I was writing there, Heather started walking here. So Juanita was walking for 1, 2, 3, 4, 5, 0.1 hour. Okay? That's what I put over there. Now, if they want to know the distance that Juanita had covered when Heather started walking, then you go over here to Juanita's graph, because this is Juanita's graph, and then you move to the left and you will find the distance. Okay, I think that's the next question. Okay. What was Juanita's position at 0.2 hours? Okay, one more time. So it was 0.2. So in 0.2 over here, I go here to Juanita's graph all the way. I'm going to say 0.9 kilometers. Okay, let me put that over here. So Juanita's position. Oh, I'm going to put that over here. Juanita was, remember that you are giving direction, 0.9 kilometers, unit of measurement that you have there, away from the origin. We don't know if that position is west, if that position is east, because we don't have information. Okay, they say, at what time was Heather 5 kilometers from the start? These questions are super fun. 5 kilometers from the start. Okay, this is Heather over here. 5 kilometers from the start, and then you go down. Let me see. What was the question one more time? At what time was Heather 5 kilometers from the start? 5 kilometers. Okay, over here. If I go down, this is 1.5, 1.6, 1.7. Okay, 1.8. That would be like 0.25. Heather points. See over here, Heather was 5 kilometers from the start. After I'm gonna say that is 1.73 hours. Here I'm using significant figures because I'm estimating the number, because you don't have that information there. 1.7 1 point, because it's not exactly 1.7. 1 2 3 4 5. This is 6 7. It's not exactly 1.7, but 1.7 can be accepted in there, so you don't have that number in there. When you have problems like this on a test, then it's gonna be easy for you to identify the numbers. Okay, now as you can see, this is an example. Okay, an example that you have over here. You have two lines that they were in. They are not parallels, but they are going away from each other. Do you have an intersection point over here? You don't have an intersection point. So if you have two runners or two walkers that are moving in following the pathway or parallel lines, are they gonna meet at some point? The answer is no. Okay, now if you have okay, two runners, runner 1 and runner 2, see that they are following this behavior, at a point in there they're gonna be able to meet. Okay, if that point can be found using the graph, it can be found using the solving a system of linear equation given by the equation of the two lines. Okay, but this lesson is super easy. The only thing that you have to do when you have a position versus time is just to get information from there. We are gonna get into this when you learn about speed. Questions? You don't have any questions? Okay.